You know when you hear a news report about a new power plant and they start throwing around terms like megawatts, gigawatts, and megawatt hours, it can feel a little murky, right? Well, we're going to clear all that up. The language of electricity can seem confusing, but trust me, once you get it, you unlock a whole new way of understanding everything from your power bill to the big headlines about our planet's future.
But first, let's talk about the stakes here. Because when we get basic measurements wrong, the consequences aren't just big. They can be, well, literally astronomical.
Take this, for example. Back in 1999, NASA's Mars Climate Orbiter, a cool $125 million mission, was closing in on the red planet. But instead of gracefully entering orbit, it just got too close. It burned up and completely disintegrated in the Martian atmosphere. A total loss.
And then there's the absolutely wild story of Air Canada Flight 143. We're talking about a brand new Boeing 767. In 1983, it just ran out of fuel. At 41,000 feet, all of a sudden, a 100-ton passenger jet became the world's biggest and quietest glider.
So you've got a lost space probe and a plane just silently falling out of the sky. What on earth could possibly connect these two totally catastrophic failures?
Well, the answer for both is shockingly simple measurement errors. I'm not kidding. For the Mars orbiter, one team was using metric units and another was using imperial. For the jet, the flight crew calculated the fuel in pounds instead of kilograms. It just goes to show you, getting your units right isn't just for a high school science class. It has massive real-world consequences.
To stop these kinds of billion-dollar, life-threatening mistakes from ever happening, there's actually an entire field of science dedicated to, you guessed it, getting measurements right.
It's called metrology. It's the science of measurement. And its whole goal is to create a global standard, to make absolutely sure that a kilogram in Canada is the exact same kilogram in the US, so that huge, complex projects, like, say, building a space probe with teams all over the world, don't end in fiery disaster. Okay, so in metrology, there are two really important words that people mix up all the time: accuracy and precision. Let's start with accuracy. Just think of it like this. How close is your measurement to the actual true value? And this archery target is the perfect way to picture it. An accurate shot, or an accurate measurement, hits the bullseye. Simple as that. It's right on the money.
Precision, though, is a little different. It's not about hitting the bullseye itself. It's all about consistency. It's about how close your repeated measurements are to each other every single time you do it.
And this slide just illustrates the difference perfectly. Look at that. See that super tight grouping of arrows on the target? That's precision. The measurement is repeatable, it's consistent. But notice how they've all totally missed the bullseye? That's a lack of accuracy. And that's the scary part. You can be very, very precisely wrong. Which is pretty much exactly what happened with that Mars probe. So the solution to this huge global problem is thankfully a global agreement, the International System of Units, or just SI. You can think of it as the world's shared rulebook for base units like the meter, the kilogram, and the ampere. This system is what allows scientists and engineers everywhere to be both accurate and precise, because everybody is aiming for the exact same target.
Okay, so we've established why precise, accurate measurement is so critical. Now, let's take that idea and apply it to one of the most important things we measure in our society, the creation and flow of electricity.
Almost all the electricity that we use today comes from a pretty simple principle discovered by Michael Faraday way back in 1832. It's called electromagnetic induction. Basically, it just says that if you move a magnet inside a coil of wire, you create an electric current. That's it. The key is movement, or to put it simply, spin.
And boy, have we gotten good at creating that spin. A modern gas turbine, for instance, is basically a controlled, continuous explosion. It sucks in air, compresses the heck out of it, mixes it with fuel, and ignites it. And then it uses that massive expanding force to spin turbine blades. And those blades, they spin a generator, turning that simple principle from 1832, that simple spin, into the electricity that powers our entire lives.
So a generator spins and makes electricity. Easy enough. But this brings us to a really common point of confusion. How do we actually measure the electricity that spin creates?
This question, which was pulled right from a Reddit forum, gets right to the heart of it. If a giant dam has a capacity of, say, 22,000 megawatts, is that per day, per month, per year? Why isn't there a time unit attached? And it's a fantastic question because it shows just how easily we mix up two very different but related ideas.
Okay, here's the key that unlocks this whole thing. All the confusion comes from mixing up power and energy. The best analogy is your car. Think about it. Power is like your speedometer.
It tells you your speed right now, at this instant, say 100 kilometers per hour. Energy, on the other hand, is like your odometer. It tells you the total distance you've traveled over your whole trip. You would never say your car has a top speed of 150 kilometers per hour, right? Of course not. The time is already baked right into the measurement.
So when we apply that same logic to our electricity units, it all becomes crystal clear. A megawatt, or MW, is a measure of power. It's the rate of electricity flow at any single moment. It's the speedometer. And a megawatt hour, or MWH, is a measure of energy. It's the total amount of electricity produced over a period of 1 hour. It's the odometer.
And that brings us right back to that original Reddit question. When a news report says a plant has a capacity of 22,000 megawatts, they're talking about its maximum power output, its top speed. It doesn't mean it's cranking out that much every second of every day, any more than you drive at your car's top speed all the time. It just means that's what it can do at its peak. The total energy it actually produces over a month, well, that would be measured in megawatt hours.
All right, so we've untangled the technical terms. But why does any of this really matter in your day-to-day life? Why should you care?
Well, because understanding this difference is actually crucial to be an informed citizen. When you hear a politician make a big promise about a new power project, or you read a report about the stability of the energy grid, you can now ask the right questions. You can spot the difference between a promise of power and a delivery of energy.
And this quote from the National Physical Laboratory really brings us full circle. From the GPS that got you to where you are today, to the smartphone in your hand, precision measurement is the invisible foundation of our modern world. It's something we rely on constantly, even when we don't realize it.
So, I'll just leave you with this question to think about. Now that you know the difference between power and energy, how does that change the way you read headlines? The next time you see a story about a massive new solar farm, you'll know to ask, are they talking about its peak power on a perfectly sunny day, or the total energy it can reliably add to the grid over a whole year? Knowing that distinction, well, that's the first real step to truly understanding our energy future.